turn on your phone, flip a light switch, maybe even rely on a pacemaker. Ever stop to think about what's behind it all? That intricate dance of electrons making it all work. It's a symphony of electrical engineering. And that's the world we're diving into today.
It really is amazing, isn't it? How we interact with the end results, the light, the sound, a phone call. But most people don't even think about the complexity behind it. They picture some lone engineer hunched over a workbench soldering pieces together. But the reality is it's much more intricate, and honestly, it's way more exciting.
Right, we're talking about everything from the tiny transistors on a microchip to the massive electrical grid that powers a city, all of it meticulously designed. But where do you even begin with something like a microchip? How do you approach something that complex?
Well, the foundation of any circuit, big or small, is the specification. That document is like a blueprint. It outlines the purpose, the functionality, all the limitations of the circuit. It's not just, hey, make this thing work. It's about making sure it works within very specific parameters like voltage and power limits. Even things like, environmental factors have to be considered. Think about it. Designing a circuit for a car is totally different from designing one for a pacemaker. The requirements are completely different.
So it's not just connecting the dots. You need to understand the entire ecosystem the circuit will be operating in. But how do you keep a project from spiraling out of control? Like you start remodeling your bathroom and end up adding a second story to your house.
Oh, that's where we talk about design creep. It's this tendency for projects to just expand beyond their initial scope. You have these unrealistic goals, or maybe there's miscommunication, and that can lead to a circuit trying to do too much, or even worse, end up doing the wrong thing altogether. A well-defined specification, though, that keeps everyone on the same page. It prevents those costly redesigns down the line.
Okay, that makes sense. So say we have a solid specification. Do we jump right into schematics and parts lists then?
Not so fast. This is where the real creative problem solving comes in. Imagine starting with a black box. It represents the whole circuit's function, and then you break that box down, smaller interconnected blocks, each with a very specific job.
Okay, so that's how you make a complex system manageable. Break it into smaller pieces. But those smaller blocks, they still need to be fleshed out, right?
Exactly. That's where the magic happens. You determine the exact electrical functions needed, research the right components, and run simulations to make sure it's even feasible. It's a lot of back and forth, testing assumptions, tweaking values. Sometimes we even have to scrap whole sections if they don't meet the specs. Can't forget we're dealing with the laws of physics here. No amount of wishful thinking will change that.
Sounds like a constant balance between creativity and, well, the limits of the physical world. But I imagine there's also this pressure to keep costs in check. Does a fancier component always equal a better circuit?
Not necessarily. Every decision you make in the design phase has ripple effects. It impacts the performance, the budget, something as small as choosing between two different transistors. That might affect the overall cost, the production time, even how long the circuit lasts. The design phase, it often ends up being the most expensive part of the whole process, way more than actually manufacturing each unit.
It's like investing in a good architect for your house. Spend more upfront to get a better, more efficient design. Saves you money in the long run. But even with all that planning, can you really anticipate every challenge before you start building?
That's where verification comes in. We use math, computer simulations to catch any potential problems before they show up in the real world. Think of it like catching a typo in a book before it gets printed.
Avoid a whole batch of misprinted circuits. I like that. So that brings us to the point where the design, which is all theoretical, needs to become a real physical object. What happens then?
We move from the abstract to the tangible. It's time to choose the actual parts that will make the design come alive. And this, let me tell you, this is no easy task. We're not just picking things out of a catalog. We have to think about their size, how they'll fit onto a printed circuit board, their heat tolerance, how they'll interact with other components.
I bet that can get overwhelming quickly, especially with thousands of options for each part. It's like a massive 3D jigsaw puzzle, except with electricity, and a lot more at stake.
You got it. And there's another layer. Standardization. Not every resistor value you might want, it doesn't always exist. So we have to design with what's actually available. It just shows how iterative this whole process is.
So even with all the fancy design software, there's still a huge need for human ingenuity to navigate all those complexities. This has been an incredible conversation, really eye-opening. It's fascinating to learn about a field that most people don't even think about, but it's so fundamental to our modern world. And don't forget, if you enjoyed this conversation, subscribe to our channel for more discussions on the cutting edge of technology. Hit that like button and leave a comment below with your thoughts and questions. We'd love to hear from you. Until next time, keep those circuits firing and those minds exploring.